Hello and welcome to a very important topic in our general pathology series that involves a very important phenomenon by which the cell is able to properly get rid of itself, properly dispose of itself in a way that does not harm the surrounding, in a way where the cell membrane is intact and the intercellular content of the cell does not leak out of the cell and cause inflammation. So let's not get ahead of ourselves, but let's begin by just outlining the important topics that we will discuss in this very important episode. Okay, so we first have to define what apoptosis is. Apoptosis is a manner by which the cell activates, initiates, triggers its own death by activating biochemical pathways that work in a cascade that culminates in the death of the cell. So it's an active process. So we will talk about that. We will also talk about the different mechanisms or the different pathways, the two main pathways by which the cell is able to perform and execute this phenomenon known as apoptosis. Being the first pathway is the intrinsic pathway involving the mitochondria. It's very obvious that because the mitochondria is inside of the cell, so that pathway involving the mitochondria leading to the cell death is called the intrinsic pathway. So the mitochondria has many important functions, the powerhouse of the cell. In addition to these many functions of aerobic respiration, we also have the mitochondria being responsible for cell death. So this is the intrinsic pathway of apoptosis, initiated and carried out by the mitochondria. There is another pathway known as the extrinsic pathway, where an extrinsic extracellular receptor known as the death receptor is sitting out and waiting for death ligand, death stimulus, death stimuli or death signal that comes from particular cells. Later on we will know that these cells are the lymphocytes of the immune system. They will come bearing those death signals and they will bind that death receptor, and upon this interaction where the death ligand binds the extrinsic death receptor, an intercellular pathway, intercellular cascade is initiated involving intercellular adaptive proteins that culminates into cell death. So we will also talk about, although we have two different mechanisms, two different pathways, an extrinsic pathway involving an extrinsic death receptor pathway and an intrinsic pathway involving a mitochondrial pathway, in the end, these two different pathways, they have to converge. They have to converge in the activation of proteases, degradative enzymes known as caspases. No caspases, no apoptosis. There will be no apoptosis, there will be virtually no apoptosis without the activation of the caspases by either pathway, extrinsic pathway or intrinsic pathway. Both of them, although their triggering mechanisms, their activities are different, but their end process is to activate these caspases. And lastly, we will talk about, after the activation of the caspases, there will be cytoskeletal degradation of the cellular components, and there will be endonuclease activity where the DNA of the cell will be fragmented, the nuclear membrane will be fragmented, and we will see morphological features like condensation of the chromatin content of the cell known as pycnosis. We will see also a process called karyorrhexis, where there will be a degradation of the cell's nuclear membrane. There will also be a decay of the mRNA available in the cytosol. There will also be condensation of the cytoplasm. And lastly, and the most important morphological feature, is the blebbing, or the budding off, or the creation of these vesicles, where the big cell will fragment into vesicles enclosed within an intact cell membrane. And lastly, there will be a very important role played by the immune system's macrophages. So the macrophages would come triggered by some soluble substance that is released by these apoptotic bodies, these apoptotic vesicles, these apoptotic blebs. And then the macrophage will come and it will engulf and gallop and swallow these cells. And most importantly, the macrophages will detect a signal on the surface of these apoptotic bodies, these edible apoptotic bodies, edible apoptotic blebs. And how does the macrophage knows that these blebs are to be eaten and engulfed? So there is a signal, and that is a protein called phosphatidylserine. Phosphatidylserine is available inside the inner leaflet of the cell, but when the cell undergoes apoptosis, that leaflet, that phosphatidylserine that is normally localized into the inner leaflet of the cellular membrane, it will be extroverted, it will be put externally. So from an inner leaflet, it will go on the outer leaflet. And when that phosphatidylserine is flipped into the outer side of the cell, it functions as a flag calling these macrophages to come and swallow and engulf and gallop these edible apoptotic bodies. So as we will talk about these concepts, it will make more sense. So now let us go ahead and review our chain of events that we have covered so far, and actually let's go ahead and find where exactly does apoptosis fall. So let's do that. Okay, so we talked about a cell being in homeostasis. A cell in homeostasis, a normal cell. This normal cell becomes a target of a stress. A stress is a negative thing. I forgot to put a negative sign. Where's my red? Where is my red marker? That is my red marker right here. So stress is a negative force that causes the cell to deviate from its homeostatic range. And stress could be external to the cell, or could originate from the outside of the cell or the inside of the cell. An example of a stress originating from the outside of the cell, like ultraviolet radiation, trauma, or a infectious agent like bacteria or fungi or viral infection or parasite infection. And these external stresses would accumulate, these external origins of stress would lead to a stressful force that leads the cell to deviate from its balanced homeostatic steady state. Or we can have another source of stress, that is the internal stress, and it is usually a consequence of a genetic defect where the there would be an accumulation, for example, of misfolded proteins due to a genetic defect where the proteins responsible for the proper folding of the cell are no longer working. So there will be a stressful stimuli caused by this abrupt accumulation of misfolded proteins. Also, another a form of intercellular stress could be caused by a genetic defect that causes a defect in a protein responsible for DNA repair. So there will be accumulation of damaged DNA. There also could be a genetic defect leading to inborn errors of metabolism and accumulation of toxins as a result. So either way, an internal cause of stress or an external cause of stress would culminate into a stressful stimuli that presents as a challenge to the cell's homeostasis. Now, the cell would fight back by adaptive mechanisms. If these adaptive mechanisms succeed, that would be a positive thing, and we would return right back to being a normal cell in homeostasis. Otherwise, if these adaptive mechanisms fail, we would have cell injury. We already talked about what are the factors that affect whether the adaptive mechanisms of the cell would win versus these stressors, and what are the factors that would cause these stressors to defeat the adaptive mechanisms. And we talked about onset. If the onset was very rapid, if the stimuli was very strong in intensity, if the cell was actually a feeble or weak cell. So these factors would lead into the cell into the cell becoming an injured cell, and now we'd have cell injury. So if we have cell injury, that injury, the cell could come back and reverse that injury through additional adaptive mechanisms, and that is a positive thing. We put it into green color, and then we would go right back into being a normal cell. From an injured cell, that is reversed, and we would go right back into a normal cell. But if the cell is injured beyond repair, and remember we talked about a very important phenomenon, and that is the nebulous point of no return, a point beyond which the cell is injured beyond salvage, that is damaged beyond salvage. The cell can no longer be repaired, and that injury will be called irreversible injury. So if there is an irreversible injury, then there will be a commitment to cell death. So now the cell has to die. Now, how will the cell die? Will it die in a positive manner? I put it into in a green color. So apoptosis is a mechanism by which there is a cell death, a positive death, by which the cell is able to properly get rid of and properly dispose of itself without harming the surrounding, and then the tissue will undergo proliferation. We will have new cells, new normal cells in a state of homeostasis. Or will the cell death happen by a very vicious and very abrupt mechanism called necrosis that we will talk about? After necrosis, if necrosis takes place, it's a vicious and a sudden event that would immediately lead to acute inflammation and then chronic inflammation and so on. So the reason why we have apoptosis is to ensure that we go right back into a normal cell, instead of having inflammation. So apoptosis protects the cell and the body from the cell, this dying cell, eliciting inflammation. This dying cell has to be properly properly disposed of in a way that does not elicit inflammation. Obviously, and the most important thing is to make sure that the cell membrane remains intact and the intracellular content does not leak out, as what happens in necrosis. In necrosis, there is no cellular membrane that is intact. In apoptosis, we have the cytoskeletal rearrangements where the cell breaks into buds into edible bodies, into edible apoptotic bodies that are later engulfed nicely by the macrophages, as here these edible bodies would break off. These edible bodies would break off, and then the macrophage would recognize them and gallop and engulf and swallow them and properly degrade them. And now we have gotten rid of this big cell that became injured and died and broke off into little vesicles that would later be taken by the macrophage, and now we have no cell, the membrane is intact and nothing leaked. Okay, so now let us move into the most important pathways by which the cell is able to perform apoptosis or programmed cell death. Now let's imagine that this is a cell, and we have two pathways. I will talk about the first pathway, and then we will talk about the second pathway. The first pathway, as shown here, if you excuse me, this pathway, I have drawn this line right here to show you that there's two different pathways. So the right pathway with this big mitochondria, excuse my drawing, my drawing that is not very artistic. This right here is the intrinsic pathway, and this right here is the extrinsic pathway. And as you see, I have them both converging into the activation of caspases. So let me go back and make some very important highlights. Okay, so this pathway here, we would call that the intrinsic pathway. And this pathway here we would call the extrinsic pathway. And as you see, there is an extrinsic death receptor of the tumor necrosis factor type 1, and a ligand will come and bind, leading to the activation of intracellular adaptive proteins that trigger a cascade that culminates into the activation of caspases. Now, let's look here for the intrinsic pathway. Something that is very important to know, and that is the intrinsic pathway is the main pathway by which cells undergo apoptosis. So 90% of the time, if a cell died, you be sure that it died through the intrinsic pathway. That is the main pathway by which the cells die. And the extrinsic pathway is the minor pathway, the rare pathway by which the cell dies. So let's examine what happens here. So in a normal situation, apoptosis happens, as we said, due to the activation of caspases. So we need to activate caspase. So who activates caspase in the intrinsic pathway? It's a very important protein called cytochrome C. Once cytochrome C is activated, caspase cascade will be activated, leading to the degradation of the cells and the commitment to an apoptotic pathway involving endonuclease activity, fragmenting of the nuclear membrane, karyorrhexis, condensation of nuclear chromatin known as pycnosis, and decay of mRNA, and this cytoskeletal breakdown in a way that makes the cell turns into blebs or buds, apoptotic buds or apoptotic blebs or apoptotic edible bodies that will be taken. So let's go back into the intrinsic pathway. So cytochrome C activates caspase. Well, who then activates cytochrome C? Well, normally in normal situations where the cell is alive and well, cytochrome C is sequestered inside the mitochondria. It is locked inside the mitochondria, because if cytochrome C leaves the mitochondria you rest assured that the cell is going to die, because cytochrome C will immediately turn on and activate these caspases. Now, it's very important also to know that in order for cytochrome C to activate caspase, it has to leak out through a channel. It has to leak out through a channel. Who makes that channel? That channel is made by the dimerization of two different proteins, Bax and Bac. So Bax and Bac would dimerize to make like a cylinder, or to make like a cup that is open on both ends, and it will insert itself into the mitochondria, causing a permeability in the membrane of the mitochondria, through which cytochrome C would leak out, and it will go and it will activate caspase, leading to apoptosis. Now, in a normal situation, cytochrome C is sequestered and there is no channel. The membrane is intact. When there is pro-apoptotic signals, pro-apoptotic stimuli, or anti-survival signals, if there is anti-survival signals or pro-apoptotic stimuli, then Bax and Bac would be activated. So let's go to the normal cell. Let's go to the normal situation. In a normal cell, cytochrome C is sequestered, locked, and imprisoned inside the mitochondria. Why? Because there is a very important family of proteins known as the BCL proteins, but namely the two proteins are one, BCL2, the second one is BCLXL. You need to know these two proteins, BCL2 and BCLXL. What do these proteins do? You see, they inhibit the dimerization of Bax and Bac. So the channel will never be formed as long as BCL2 and BCXL are active. If BCL2 and BCXL are active, they would inhibit Bax and they would inhibit Bac from dimerizing and becoming a channel that would insert itself into the mitochondria, leading to the escape and leakage of cytochrome C that would later on activate caspase. Now, let's say the cell understood that it must commit to programmed cell death, that it must kill itself. What happens? There is a very important sensor that you need to be aware of, called the Bh3 sensor that I drew here in yellow and blue. This Bh3 sensor, what does it do? It senses internal stress from the inside. You see my arrows? One arrow is from the inside. And external stress, as external stress. So if the cell undergoes ultraviolet radiation, trauma, infection, increased temperature, any source of stress that originates from the outside of the cell, it will be sensed by Bh3. Or if there is an internal stressful stimuli, such as accumulation of misfolded proteins caused by a defect in the protein that causes them to be folded properly, or if there is over accumulation, or there is increased amounts of reactive oxidative species caused by the disappearance or inactivity of the enzyme, for example catalase, that is responsible for properly getting rid of these reactive oxidative species and turning them, for example, into peroxide. So now there will be an increased amounts of reactive oxidative species that would cause internal stress and DNA damage. Many of these internal stresses, they will be sensed by Bh3 sensor. Now, if the stress is if the stress causes cell injury, and the cell injury is irreversible, and the damage happened beyond salvage, and we have passed the point of no return. The cell must die. It cannot be repaired. The injury is irreversible, then it will be sensed by Bh3 sensor. Now, if the Bh3 sensor is activated, then the Bh3 sensor will over jump the BCL2 and the BCXL proteins that inhibit BAX and BAC, and Bh3 sensor would immediately activate BAX and BAC. BAX and BAC would dimerize, BAX and BAC proteins would dimerize. When BAX and BAC proteins dimerize, they would make for us a channel like a pore, and it will insert itself into the membrane, leading to increased mitochondrial permeability. Cytochrome C would come out, leak out. It's cytochrome C and additional pro-apoptotic proteins that would come out. It's not like it's only cytochrome C. So cytochrome C would come out and a leakage, and then it will go right into activating caspase. And when caspase is activated, we would have cytoskeletal breakdown and rearrangement, leading to the formation of apoptotic bodies, apoptotic blebs, apoptotic buds that are edible by macrophages. Okay? And there will also be endonuclease activity that causes karyorrhexis, which is the breakdown of nuclear membrane, and it will also cause condensation of chromatin, known as pycnosis, and there will also be degradation of any nascent or ready mRNA protein. It will cause the decay of mRNA transcripts, and then the cell will start to bud off and make vesicles, and these vesicles would be sensed by macrophages. I have drawn this yellow protein is in the inner leaflet of the membrane. Now, when there's a vesicle, it would jump outside, it would flip outside. This phosphatidylserine, this phosphatidylserine would flip out into the outer leaflet of the cell, and then after it is flipped, it's out, the macrophage, this red macrophage, would come and it would recognize this phosphatidylserine, and it would engulf and eat these vesicles expressing the phosphatidylserine. Where is my yellow marker? Where is my yellow marker? Here's my yellow marker. You see all of them? Many of them have yellow phosphatidylserine outside, yellow phosphatidylserine outside, yellow phosphatidylserine outside, yellow phosphatidylserine outside. Macrophage will come, detect there is a cell that successfully broke off. Where is my black? Where's my black? Where is my black marker? It has bud off, and it expressing phosphatidylserine outside, and then the macrophage would come and detect that yellow phosphatidylserine as a signal, as a eat me signal, as a eat me because I am an edible bleb. I'm an edible cellular bleb that is a product of apoptosis. And also, there's also soluble substance that is good enough to be recognized by the macrophage and to lead to the swallowing of this apoptotic bleb. But that soluble substance is not good enough to elicit inflammation. So how does a macrophage recognize that a cellular bleb, that an apoptotic bleb is to be swallowed? Either by recognizing the phosphatidylserine on the outer leaflet, or by recognizing some soluble molecules that come out only during apoptosis. That soluble amount is not strong enough to elicit inflammation, but however, it is strong enough to be recognized by the macrophage, leading to the engulfment and swallowing of these apoptotic blebs by the cell. Well, let me see if I'm still, yes, I'm still on. Okay, now let's talk about the TNF or death receptor pathway. Now we have death, this right here is the death receptor pathway. The death receptor pathway, how does it happen? It is the pathway that involves the lymphocytes of the immune system. So now imagine all the cells have an outer death receptor that is inactive because it is missing a ligand. The lymphocytes, if that cell was determined to be killed, and that can happen in a situation where an inflammation has finished and there is an excess and leftover amounts of lymphocytes or cells that if they are left there, they would cause positive feedback and even more inflammation. So what happens is the lymphocyte would come and it has that key, it has that ligand. It's called the FAS L ligand. That FAS L ligand would come and bind into that extracellular receptor. That extracellular receptor would then, upon the binding of that FAS L ligand to that TNF1 receptor, there will be an activation of adaptive proteins and intercellular signaling cascade that culminates into the activation of caspase. Okay, a very important thing you need to know. Although both intrinsic pathway, mitochondrial death pathway, activates caspase, they activate a caspase that is subtype 9. Caspase 9. Caspase 9. While the extrinsic death receptor pathway would activate a caspase of the subtype 8. So if you see there is in lab, there is a lot of caspase 9 in the cytosol, you know that cell is dying through the mechanism of intrinsic pathway or mitochondrial death pathway. If you see caspase 8, which is another subtype of caspase, you will see that this was caused by extrinsic or extracellular death receptor pathway or the extrinsic pathway. Now, what does caspase do? Caspase is a degradative protease that cuts and cleaves beyond or after the aspartic acid amino acid. So it cleaves and breaks proteins inside the cell, degrades these proteins. How? By cutting and cleaving by its endonuclease domain, destroying all these proteins right after the aspartic acid residue. Then the protease would initiate endonuclease activity. We talked about karyorrhexis, breakdown of nuclear membrane, as we see right here, breakdown of nuclear membrane, karyorrhexis, condensation of chromatin, pycnosis, and degradation of cellular structures and formation of edible apoptotic bodies. And so pretty much in intrinsic pathway and extrinsic pathway, once we reach the caspase activity, then the process is universal. We would have endonuclease activity, breaking down and cleavage of cellular components, and cytoskeletal breakdown and cytoskeletal rearrangements, where there is ensuring that the cellular membrane remains intact. Another interesting thing that you need to know is that the name of the protein, for example, that flips this phosphatidylserine from the inner leaflet to the outer leaflet is called the scramblase. Scramblase. Okay, if you ever on Who Wants to Be a Millionaire. Okay, then so the process is pretty universal from caspase activation and onward. So there will be, as I said, endonuclease activation leading to the breakdown of nuclear membrane and destroying the DNA and cytoskeletal rearrangements, condensation of chromatin, and cytoskeletal rearrangements leading to the formation of edible apoptotic bodies, edible apoptotic blebs, edible apoptotic buds, and these buds are recognized by the activity of scramblase, where phosphatidylserine is flipped from the inside to the outside, working as a flag, calling the macrophages to come and swallow these cells. And this happens, so once this caspase is activated, then as I said, the process is universal. The macrophages will come and will eat these edible blebs, irrespective of whether they were created. These blebs were created by intrinsic pathway or extrinsic pathway. Okay, so once you have a bleb, it's very difficult to know how did that bleb form. Did this apoptotic bleb form as a result of intrinsic pathway or extrinsic pathway? It's very difficult to know. But however, if we go back into the cell and we see cytochrome C, you know that's a feature of intrinsic death pathway. If there is a Bax activation, you know very well that it would lead to if there's an increase in mitochondrial permeability, some substance leaks out, you know that is a feature of intrinsic death pathway. If there's activation of Bh3 receptors, you know that's a feature of intrinsic pathway. If there's immune cells leading, and that if there's caspase 9, that's also a feature of intrinsic pathway. But if there's fast ligand or tumor necrosis factor receptor, death receptor activated by this fast ligand, that's a feature. If there's adaptive proteins activated by the fast ligand by the fast L ligand, activating TNF1 receptor and leading to the activation of caspase 8. So I see that maybe they're gonna ask you the intrinsic pathway would lead to the activation of which caspase, 7, 8, 9, or 10. So you just say 9. 8, that's caspase 8. That's a feature of extrinsic pathway. But as soon as caspase 8 or 9 are activated, there will be one cytoskeletal breakdown of or organelles in the cell, and rearrangement of the cytoskeletal components, these actins of the cellular membrane, because it needs to be intact. So it's an active process. So apoptosis is an active process requiring ATP, requiring oxygen. So that's why hypoxia would usually lead to death by necrosis. Hypoxia rarely leads to death by apoptosis, because oxygen, aerobic respiration, is very important in this process that, you know, this programmed cell death apoptosis needs ATP, needs oxygen in order to fully carry out the proper disposal of itself through the activity of biochemical pathways leading to programmed cell death. The last thing I want to leave you with is that, remember we talked about whether or not we should put cell death in red as a negative thing. Is cell death a negative or a terrible connotation? You know, we have physiological apoptosis and we have pathological apoptosis. We should not always have the impression that apoptosis is pathological as a result of some stress, an internal stress or an external stress. No, sometimes apoptosis could be physiological. So during embryogenic development, okay, or some cells must die in order for us to function properly. When we are born, the cells between our fingertips and toes are intact. So they must die. They die through apoptosis in order for us to be able to use our fingers and may use a calculator, for example. So now, without apoptosis, this is a form where apoptosis functions as a physiological thing. So this is something that we need. So the cell between our fingertips die. How do they die? There is always pro-apoptotic signals. Pro-apoptotic signals. And there are also anti-apoptotic signals. The anti-apoptotic signals are pro-proliferation or anti-proliferation. If you are pro-proliferation, that means you don't need to die. if the cell receives growth factors, pro-proliferation signals. So that means this is an anti-apoptotic event. Okay, let's see. We have a seesaw. Okay, this seesaw has a negative or a positive component. If the negative or the negative is represented by pro-apoptotic signals or anti-proliferation. So if the cell has more pro-apoptotic and more anti-proliferation, the cell will die. However, if the cell has pro-proliferation, meaning it will proliferate, pro-proliferation and anti-apoptosis, then it will survive. There's survive versus death in our seesaw, the death seesaw. In this death seesaw, seesaw. So what happens is, if there is pro-proliferation and anti-apoptosis, the cell will live. If there is pro-apoptosis and anti-proliferation, this is a process governed by the growth factors. So our cells in physiology, in normal development, these cells between our fingertips, what do you think they would receive? Do they receive growth factors that promote proliferation and anti-apoptosis? No, otherwise they would have stayed on and our fingers would have been like that, stuck together, and toes also. But because they receive growth, they don't receive growth factors for proliferation, and in fact they receive signals that promote apoptosis, then they would start dying off, and then we would be able to have our fingers. So it's a concept that is also physiological, so don't have a connotation that apoptosis is always pathological. I tried to cover this concept as rapidly as possible, so if you can stop the video and make sure you go over these concepts again, this is a very good step for us into our direction of understanding apoptosis. I hope you understood very well, and I hope you enjoyed, and I'm sorry for any shortcoming, and I hope that you are able to benefit. Thank you very much, and I'll see you in the next video.